Hello, I'm Andrew Purvis. I'm General Manager, Europe, Middle East, Africa at the Global CCS Institute. Welcome to this webinar today, which the Global CCS Institute is presenting. This is the latest of a series of webinars aiming to keep you up to date with learning from experts from across the CCS chain from around the world. I would like to welcome our audience to today's webinar. We have an international audience with participants from right around the world. You're very welcome, and thank you for joining us. Today's webinar covers the Shell Peterhead CCS Project, Understanding Full Chain CCS Operations. This webinar follows another recent webinar that was presented by Shell, which introduced the Peterhead project. This is a full chain CCS project located in Scotland in the UK, and that webinar is available on our website if anybody would like to review that. Today's webinar aims to describe some aspects of the work that were carried out as part of the Peterhead FEED, front-end engineering design study, by PS Enterprises, who they undertook a modeling study really looking at dynamic operation of the full CCS chain. The objective of the study was to validate control systems and to understand how different parts of the chain will react during transient or other unexpected events. The team today will describe the task, the approach that they took to that, and the results of their study. I would like to take a moment to introduce you to our presenters, Alfredo Ramos, Adekola Lawal, and Penny Stanger. Alfredo Ramos is a mechanical engineer. He studied at RWTH in Aachen in Germany and graduated in 2000. He subsequently went on to study for an MBA at London Business School. He's currently Vice President Power and CCS at PSE, where she's been since 2006. Our other presenters are Adekola Lawal. Dr. Lawal has a PhD in post-combustion CO2 capture for coal-fired power generation from Cranfield University. He's worked previously for Parsons Brinckerhoff as a CCS engineer, and he's now a senior consultant with PSE's Power and CCS group, having joined PSE in 2012. Our final presenter is Dr. Penny Stanger. Penny's PhD was in modelling and simulation of oxyfuel combustion, which she attained through the University of Leeds. Her previous roles have been in plant modelling with the utility company E.ON and operational research at Her Majesty's Revenue and Customs, which is the UK Tax Office. She's a consultant with PSE Power and CCS Group and has been with PSE since 2014. As we go through the webinar, all attendees are welcome to submit questions. These are submitted through the Questions tab on the GoToWebinar control panel, which should be located on your screen. The questions that we get in through the presentation will be moderated and posed to our panelists together and our presenters together at the end of the presentation. Please do be aware we might not be able to get through all the questions today. However, we will try and get through as many questions as we can during the webinar as scheduled. So without further ado, I would like to hand over to our first presenter and begin the presentation.
Perfect. Many thanks, Andy, for the kind introduction. Welcome everyone to this webinar titled the Shell Peterhead CCS Project, Understanding Full Chain Operations. We have a dense program ahead of us today, so I would like to start by sharing an overview of this talk. After an introduction to PSE, which I promise will be very brief, I'd like to provide some background on gCCS and the CCS System Modeling Toolkit project before passing on to my colleagues Ade Lawal and Penny Stanger. Ade will provide an overview of the process models we developed for the Peterhead CCS project, and Penny will present the corresponding simulation results. Finally, I shall take over proceedings to provide some concluding remarks. Process Systems Enterprise is a spin-off for Imperial College in London. In 1997, PSE acquired the rights for the advanced process modeling platform gProms and established itself as a private independent company. About 10 years later, PSC won the Royal Academy of Engineering's MacRobert Award for its innovative gProm's advanced process modeling software that helps process industry companies to maximize product quality, minimize production costs, and control environmental impact, as well as enabling companies to innovate much faster, design more efficient processes, and manage risk closely. Since then, we have experienced substantial growth, achieving a global presence. Our business is split in software, roughly 60% of our revenue, and engineering services. While we have a focus on the process industries, the flexibility of our platform means we have quite a number of applications in sector considered a non-traditional ground for process modeling. In the last 5 years, we have focused our effort in 4 sectors, namely oil and gas, chemicals and petrochemicals, life sciences, and power and CCS. We deliver specialist engineering software and services for these sectors, all based on our gProms platform. On the power and CCS side, we offer 2 products, gFuelCell and gCCS, the latter being the result of a collaborative project funded by the UK's Energy Technology Institute. Back in 2011, the ETI commissioned the CCS Modeling Toolkit project aimed at developing a modeling and simulation environment that will encompass all elements of the CCS chain. A consortium formed by Rolls-Royce, CO2 DeepStore, E4 Tech, and European utilities E.ON and EDF set about developing this software package based on PSC's gProms modeling platform and process modeling expertise. The resulting end-to-end software package, gCCS, was launched in July last year and was used to deliver the dynamic simulation work for the Peterhead CCS project. With this, I'll pass on to Ade, who will be discussing the model development.
Thanks, Alfredo, and hello, everyone. In the next few slides, I will introduce the Peterhead CCS project and discuss the objectives of the study carried out by PSC. I'll give a brief overview of the Peterhead CCS project. As Andy mentioned, Bill Spence gave an excellent webinar on the project status last Thursday, and I'll definitely recommend listening to the recording if you have not done so already. Shell, with strategic support from Scottish and Southern Energy plc, is looking to develop the world's first carbon capture and storage project on a gas-fired power station. The aim is to capture and sequester CO2 from one of the gas turbines of the Peterhead power station located in Scotland. This is one of the 2 projects under consideration for the UK government's £1 billion CCS competition. Once operational, about 1 million tons of CO2 per year will be captured using Shell Council's post-combustion CO2 capture technology. This CO2 stream will be compressed and transported via a new offshore pipeline, which will tie in subsea to the existing Golden Eye pipeline. Now, the UK government has pledged support for both capital and operating expenditure of the successful project or projects. Operating expenses would be supported through contracts for difference based on the amount of clean electricity produced. This provides clear incentive to analyze and improve the operability of the plant. As with all commercial projects, we begin with a disclaimer. PSC was contracted by Shell in June 2014 to carry out a 6-month simulation study of the whole CCS chain operation. The study was carried out based on the latest information available at the time, covering the design, operating procedures, and control schemes of the plant. However, it does not reflect the complete details of the Peterhead CCS design, and as such, the findings and recommendations presented provide direction for follow-up work during the engineering phase. The final deliverable was to present a modeling study investigating dynamic operation of the full CCS chain to validate control systems and understand how different parts of the chain will react during transient events. To achieve this, a full chain model of the proposed Peterhead CCS system was developed, including the power plant, pretreatment unit, carbon capture unit, compression unit, as well as the pipeline, injection well, and reservoir. This was developed in gCCS. A number of relevant scenarios were then simulated, namely the startup, shutdown, and failure modes of various units. This was done considering both current and proposed operational procedures. Based on the simulation results, a high-level assessment of the control philosophy was carried out. In addition, bottlenecks were identified and recommendations for improvements to existing procedures were provided. I'll now describe the process models developed in gCCS for this study. This screenshot depicts the Peterhead CCS chain flowsheet model. The flowsheet constitutes 5 models of the major subsystems, which we will look at in more detail in the following slides. Ports on each model allow for integration between subsystems. So, for instance, flue gas from the CCGT flows to the pretreatment unit, where it could be sent directly to the GT stack, the gas turbine stack. This would typically happen during startup or shutdown operations, and we will mention a number of times in the subsequent slides about periods where flue gas is diverted to the GT stack, and this is what we mean here. Otherwise, it is cooled and passed to the capture unit to reduce CO2 emissions. The treated flue gas returns to the pretreatment unit where it is heated up before it is sent to the other stack. Steam from the power plant HRSG is delivered to the capture unit's reboiler via this stream connection. The second aqua-colored line is for the condensate return back to the CCGT steam cycle. CO2 captured in the capture unit is compressed and transmitted via pipeline for injection into the GoldenEye reservoir. So what lies beneath the power plant model? Here is a screenshot of the model of the CCGT, including the modifications for the supply of steam to the capture unit. Natural gas and compressed air are fed to the gas turbine's combustor. The flue gas generated is expanded and in the gas turbine and passes through the HRSG to generate steam before it leaves for the pretreatment unit. Now, 2 potential steam connections to the capture unit reboiler are modeled. In normal operation, Peterhead will use steam taken from the IP-LP crossover for solvent regeneration, with a small amount of condensate spray used to control the temperature in the desuperheater. In this study, a second steam connection directly from the hot reheat line in the HRSG was considered. This connection would provide additional steam during times when the steam turbine is not in operation, for example, during startup, shutdown, and steam turbine trips. Both connections will use the same desuperheater with the hot reheat steam let down using this let down valve to a suitable pressure first. To assess operating procedures, it is important to be able to predict the amount of steam available to the capture unit, as well as the composition of the exhaust gases during various operations, such as startup and shutdown. The gas turbine and HRSG are modeled and calibrated with heat and mass balance data to represent the steady state performance. Transient data from the existing power plant operation was used to customize the startup and shutdown dynamics of the plant model. Next, we will consider the pretreatment and capture unit. Now, exhaust gas from the HRSG is fed to the pretreatment unit before it enters the capture unit here. CO2 separation takes place in the absorber, and the treated gas stream is directed towards the stack here. A purified CO2 stream is produced here for compression. The focus of the study was to understand the dynamics of the CCS chain. In order to protect council's intellectual property, a representative amine solvent whose thermodynamic properties are readily available was selected for the capture process model. Now, the capture unit flow sheet you can see is the typical amine plant configuration, including the absorber, the wash water, the solvent cross-sheet exchanger, the stripper column, the reboiler, condenser, and lean amine tank. In gCCS, we model the absorption of CO2 using our proprietary dynamic rate-based pack column models. This unique feature allows the user to compare and assess CO2 capture performance in various transient scenarios. The dynamics of the solvent inventory in the unit is also considered, the holdups of solvent in the column sumps and amine storage tanks are represented. This means we can investigate what happens to the holdups and CO2 loadings in the amine loop in different scenarios. To model the cooling down of the capture unit during a shutdown, we ensured that the heat losses to the surroundings for the columns and other key equipment models were accounted for. Now, there are a number of key control schemes represented here. We reproduced the schemes directly from the design data, such as the piping and instrumentation diagrams and control narratives. I will show you some of them now. So, for instance, we have level control on the column sumps. We have a ratio control for the steam demand to the reboiler that is based on the solvent circulation rate. We have temperature and level control on the condenser, and a split pressure control on the stripper column pressure. Next, we will look at the compression unit. The compression subsystem is shown in this slide. The compression unit is represented by a single-stage compressor model. So we have CO2 from the capture plant coming in here. That's a suction knockout drum, a column section, a compressor section, I beg your pardon, a dehydration unit, and as you can see, a number of control schemes. I'll now talk you through a number of important features of this unit. If flow of CO2 to the compressor drops, the anti-surge control scheme recycles fluid through the compressor to maintain the minimum flow to prevent surge. The predicted performance curves of from the compressor vendor were imputed in the compressor section model. The dynamics of the compressor startup and shutdown were represented using shaft inertia, and the pressure in the first knockout drum is controlled by manipulating the angle of the compressor inlet guide vane. Finally, I'll present some detail on the pipeline, injection well, and reservoir. Over 114 kilometers of pipeline will transport CO2 from the compression unit to the offshore platform, where it will be injected into the Golden Eye reservoir. Over the lifetime of the project, Shell will use numerous injection wells based on the operating conditions at the time. The injection well modeled in this study represents the early phase of injection operations. Now, distributed models are used in this subsystem. This means the user can track the conditions of CO2 along the entire length of the pipeline and injection wells and carry out flow assurance studies. In addition, the pressure profile of the system is very sensitive to changes in flow rate, fluid phase, and temperature. The models account for heat losses to the environment, the effects of changes in topography and line diameters, and indicate the onset of phase changes. In addition, these models can address questions such as how much line packing is available from the pipeline. Now, that was a quick overview of the subsystems in the Peterhead flowsheet. I will conclude by describing some of the key performance indicators for the integrated system. Shell was particularly interested in how operating procedures could be optimized to maximize performance of the plant. To achieve this, we included system KPIs linked to the proposed commercial agreement, which is a contract for difference, or CFD, for units of clean electricity produced. Now, clean electricity is the cumulative sum of the product of net electricity exported and the fractional capture rate. So 90% capture, for instance. The amount of CO2 emissions avoided are obviously an important performance indicator. In the report, we quantified benefits in terms of how much additional clean electricity could be produced, as well as how much CO2 emissions could be avoided. I will now hand you over to my colleague Penny, who will present the simulation scenarios and results.
Okay, thank you, Ade, and hello everybody online. Okay, so we looked at a number of different scenarios, including how to shut down or turn down the plant, starting up from cold or hot conditions, and also how the plant could react in various failure scenarios, including a trip of the steam turbine, trip of the CO2 compressors, or an interruption to the injection process. Here I'm going to show you the results for shutdown and startup scenarios. So first of all, here's how the normal shutdown procedure will work. This graph shows the power output from the gas turbine in blue and from the steam turbine in red, which both begin from 100% load. The shutdown process begins here. The flue gas is diverted so that it's vented direct to atmosphere, and the capture unit continues to process the CO2 within the solvent before the steam supply is stopped and the CCGT shutdown procedure begins just here. This graph shows how the CO2 loadings in the capture unit change during the shutdown procedure. So the green line is the rich loading at the bottom of the absorber column here. The blue line is the lean loading at the bottom of the stripper column, just here. And the red line is the lean loading at the outlet of the lean aiming tank, just here. Once the flue gas is diverted, the loadings begin to decrease as there is no more CO2 admitted into the absorber, and the stripper continues to separate the CO2 dissolved in the solvent. Once the steam supply is stopped, the solvent inventory continues to circulate around the system, resulting in a blended CO2 loading, which you can see here. You can see that the power output from the steam turbine increases here, since the steam supply to the capture plant is reduced when we divert the flue gas. And again here, when the steam supply to the reboiler is stopped. Both these changes result in a quick increase in the loading at the stripper exit, as the removal rate reduces or stops altogether. At the end of the leaning process, the solvent inventory is left at a low CO2 loading. Moving further downstream, we can see how the compression system will behave during shutdown. The graph shows the total flow of CO2 through the compressor in green, and the amount of flow recycled via anti-surge valves in blue. Both start off at their respective normal levels, so 100% load with no recycle flow. Once the flue gas is diverted, the amount of CO2 being sent to compression quickly drops, and the control system responds by opening anti-surge valves to maintain the system performance during the solvent leaning process. Once the steam supply to the capture unit has stopped, the compressor shutdown sequence is activated, and you can see that here. So moving further downstream, this graph shows the profile of mass flow through the pipeline and the riser. So here you can see the buffer capability of the pipeline. So this line here shows the amount of CO2 flowing sent into the pipeline during the shutdown scenario. And this line here shows the amount of CO2 flowing out of the exit of the riser. So you can see, despite the change in inlet, the flow at the exit doesn't change significantly until the injection wells are shut in, isolating the pipeline. So finally, onto the injection well. This graph shows the pressure at different points in the well. So the red line is the pressure upstream of the injection choke valve. The blue line shows the pressure at the wellhead, and the purple line shows the pressure at the bottom of the well. During the shutdown operation, as the flow of CO2 into the pipeline reduces, we can actually see the well pressures do reduce slowly. Once compression has stopped completely, the injection choke valve is closed, just here. This maintains sufficiently high pressures in the pipeline during the shutdown. As the flow through the injection well drops, a significant drop in pressures downstream of the choke valve is observed. Okay, so the next thing that we did was to look at this shutdown procedure from a whole chain perspective and to try and see if some of the processes could be improved in order to increase the amount of clean electricity produced while also reducing the amount of CO2 emitted. So as a reminder, in the normal procedure, the first thing we did was to lean the solvent. Then we stopped the steam supply, and then we shut down the CCGT. The next graph shows what this means for the CO2 balance in the capture unit. So the green line here shows the flow of CO2 into the capture unit, i.e. what's coming in through the flue gas. This stops when the flue gas is diverted. However, the flow of CO2 to compression, which is indicated by the purple line, continues throughout the solvent leaning process until the steam supply is stopped just here. Now, for the modified procedure, we decided to shut down the CCGT first and to use all available steam during the shutdown procedure. As you can see from the two power output graphs, this means the shutdown process is significantly shorter and could allow the plant more time at normal operation prior to beginning shutdown. So because the proportion of the total steam generated needed for the capture unit is relatively low, the CCGT can still continue to supply steam from the IPLP crossover during this ramp down stage until the steam turbine shutdown sequence is started. In addition, in this case, we also considered the use of that additional steam supply that Ade mentioned earlier, which meant that steam is actually still available to the capture plant into the gas turbine shutdown sequence. We then used this steam to process as much CO2 as possible. So this meant that rather than divert the flue gas, we continued to process it throughout the shutdown procedure, instead of venting it direct to atmosphere. As you can see from the green line here, which shows the flow of CO2 sent to the capture unit in this case. As the CCGT ramps down and the amount of CO2 in the flue gas reduces, we kept the steam supply constant for as long as possible, which meant that we could use some of that energy to lean the solvent. This is why the purple line, which shows the CO2 sent to compression, is above the green line here. So, and coming on to that, a final point to note from this slide is that in the modified procedure, we didn't enforce a minimum amount of solvent leaning. The amount of CO2 leaned from the solvents is roughly equivalent to the area below the purple line, but above the green line. So just here for the normal procedure, and just here for the modified procedure. The difference in leanings could impact the nature of a subsequent startup. So in summary, we assessed the impact of shutting down the CCGT first, using all available steam, including the additional steam supply, continuing to process as much CO2 as possible, and we relaxed our requirement to lean the solvent. The graphs you can see here show the effect of these different shutdown procedures on the total CO2 emitted and the clean electricity produced. So remembering back to the definitions Ade mentioned earlier, the cumulative emission is the total amount of CO2 vented to atmosphere during the shutdown procedure, which is one of the key things we're trying to reduce. The clean electricity produced is the amount of electricity produced with no associated carbon emissions. So if a plant is producing 100 megawatt hours at 90% capture rate, that's equivalent to 90 megawatt hours of clean electricity. So this is something that we want to maximise. In each case, the green dotted line shows the result of the normal procedure. So just here and just here. The green solid line shows the result of the modified procedure. So just here and just here. Finally, the black dotted line shows what the equivalent result would be if we could maintain the capture rate at 90% throughout the shutdown. So it's kind of like our target. Now, as you can see from these graphs, the modified procedure leads to lower emissions and more clean electricity produced. However, as I showed in the previous slide, not enforcing the solvent leaning stage means that the solvent leaning ends up higher. And if you remember back to the slide with the 3D pipeline plot, we also demonstrated the buffer capability of the pipeline, which is able to decouple the CCGT and capture systems from the well injection system. So moving on to startup procedures. Here we took a similar approach of first simulating a normal procedure for a cold start of all units. For this case, we also assumed that the steam supply for the capture unit is taken from the IP-LP crossover only, which is the normal procedure. We then looked at possible ideas for improving the cold startup procedure, again in terms of how to reduce the amount of CO2 emitted and increase the amount of clean electricity produced. The main changes we made were to allow the use of the additional steam connection and to begin preparing the capture unit for startup in parallel with the CCGT. So, for example, by starting the solvent pumps earlier, in order to begin absorbing CO2 from the flue gas as soon as possible. Finally, we simulated a hot start procedure. In this case, we restarted following a short shutdown. So, for example, the solvent pumps are already running and the unit is still relatively hot. In this case, we also allowed the use of the additional steam connection and otherwise followed the normal procedure. So moving on to the results. For the cold start normal procedure, here again you can see the power output for the gas turbine in blue and for the steam turbine in red. The main processes during startup, which are time consuming, are the CCGT startup time, which you can see quite clearly on the graph, and also the capture unit startup time, which can be identified from this particular graph by this point here, when the stripper begins to use the full steam supply. For the modified procedure, the power outputs look quite similar, but due to the earlier availability of the steam, and also the additional process changes we made, we're now actually starting up the capture unit in parallel to the CCGT, which reduces the overall startup time significantly. Finally, for the hot start procedure, you can see that the CCGT startup procedure itself is significantly shorter because the plant is still relatively hot. In fact, the capture unit startup is also a lot faster because the solvent is already circulating and the stripper is also still relatively hot. The earlier availability of the additional steam, again, means that we can start up both units in parallel. So coming to the summary, here you can see the impact of the modified procedure on the total CO2 emissions and the clean electricity produced for the two cold start simulations. The green dotted line again shows the results in the case of the normal procedure. The green solid line shows the result in the modified procedure. And the black dotted line shows how much CO2 we would have emitted and how much electricity we would have produced if it was possible to maintain a 90% capture rate throughout. So again, that's like the top end of our target. Now, thinking back to the previous slide, the additional steam connection allows a parallel start of the CCGT and the capture unit. And this leads to lower emissions and more clean electricity produced. We found as well that the cold start had the most scope for improvement, since the heating times within the power plant and capture unit are the main limiting factor during startup. Okay, so I'll now pass you back over to Alfredo to give the conclusions.
Excellent. Thanks very much, Penny. Now, I'd like to draw your attention to I think the key aspects of this study. I think the most relevant points are that using the gCCS flowsheet modeling package, we have built what we believe is the first full chain dynamic model of a planned CCS project. And with this, we have evaluated and validated operational scenarios. For the best baseline scenarios modeled, including full shutdown of all units and full startup from hot and cold conditions, the simulations have demonstrated that control and operation can be handled and executed safely. In addition, by evaluating and adjusting the baseline operating procedures, we also demonstrated that a substantial reduction in CO2 emissions and an increase in clean electricity production can be achieved. The most significant improvement was through including a let-down steam connection to the heat recovery steam generator, which bypasses the steam turbine. We also demonstrated the buffer capacity of the pipeline, which could allow the downstream injection processes to be safely decoupled from the upstream power generation and carbon capture for a significant period of time. Most importantly, as a take-home message, I'd like to stress that these assessments provide information to guide investment decisions and achieve cost savings both at the design and at the operational level. Finally, and to draw this presentation to a conclusion, I would like to thank all our colleagues at Shell for the knowledge and expertise and all the support that they shared, that they gave us during the execution of this project. And also my colleagues here at PSC, our gCCS team, that have put a tremendous effort on the modeling work and analysis of the result. With this, I'd like to thank you all at the other side of the line, and would like to pass on to Andy for the Q&A session.
Thank you, Alfredo. And thank you for the team at PSC for your presentation. We have been receiving questions through the presentation, but I'd just like to remind participants that you're able to enter any questions you might have via the GoToWebinar box on your website. Perhaps just before we go to questions, it's worth just clarifying that this work was carried out as a deliverable for the Peterhead FEED study, and the team are therefore somewhat limited in the answers they can give to questions they'll be talking about. Happy to talk about the modelling methodology, scenarios and results, but there are decisions that have been made by Shell, and specific details of the engineering of the Peterhead project that wouldn't be probably appropriate for us to ask them about. However, on that note, I would like to make a start with the questions, which perhaps I'll address to you, Alfredo, and you can pull in the rest of your team as required to answer them. So the first question, you mentioned looking at trip scenarios. Can you comment on what kind of trips you considered and what were your main findings regarding the impact of trips on the system?
Mm-hmm. Yeah, sure. We looked at 3 different trip scenarios: steam turbine trip, compressor trip, and loss of storage. To give more details into the different simulations that we did at this stage, I'll pass on to Penny, who has a look at who can provide a more concise view of the different studies carried out.
Okay, so yes, I know I kind of hinted at this a bit in the scenario details. So for the steam turbine and compressor trips, we looked at how the system would cope in the case of an unexpected trip, and again tried to make some modifications to see if we could deal with that in a better way. So we found, for example, in the case of a compressor trip, there was some benefits to continuing to absorb CO2 during the trip rather than immediately stopping all capture operations and venting the CO2. So what this does is it kind of builds up the amount of CO2 in the solvent ready to then process once your compressor was back online. However, we thought this potentially would only make sense if you knew the trip was going to be relatively short. For the steam turbine trip, one thing we did find is that here there's a really strong benefit to having that additional steam connection, which doesn't rely on the steam turbine being in operation. So yeah, effectively it's independent of the steam turbine. So if you have this extra steam, if you have a trip of the steam turbine, you can continue to process the CO2 and to maintain your capture rate throughout the length of the trip, which would be quite a significant benefit in that case.
Okay, thank you. What kind of insights can taking this approach and the approach that this project took, looking at systems as an integrated whole, provide that looking at systems separately, for example through specialized software designed to look at the capture plant, the injection plant, cannot? So I guess the question is, what do you get extra by taking this integrated approach?
I think I'll go for that question. Thanks, Andy. I think that's quite an important question. The CCS chain operates as an integrated system, and that means that subsystems don't operate independently of each other. So, for instance, the power station supplies steam and electricity to the capture and compression units, and if there's any disturbance in any of these three systems, this would likely impact the operation of all of them. It is virtually impossible to adequately assess the interactions between the subsystems using separate individual models. So that's why this whole chain system approach is quite key and quite important. We've also found from our experience that in even just operations like sizing the individual units of the CCS chain will be highly inefficient and a very iterative process without being able to consider the interactions between the subsystems. So what we find is that the coupling and the interactions between subsystems does affect a lot of decisions and the operation of each of the units, and as such, it's important to take all these things into consideration with the whole chain CCS model.
Yeah, if I may add as well, even for a design case, just steady state, which is a much simpler case than what we have presented here. In a previous Vladimir Mark Weidman and Paul Parsons also presented a thermodynamic study of the integration of a pulverized coal power plant and a capture unit, and he had to use, I think, if I remember correctly, and hope you can forgive me, I didn't get it right, but it was about 4 different software packages, and that had to be integrated manually, which, let's say, from a more precise point of view, just a workflow that engineers have to go through, is also a substantial overhead.
Yes. So the question was, why is the compression train modeled as a single stage, whereas in reality there'll be a number of stages, and how are the interactions between those compression stages modeled?
I think I'll go for that question. Yeah, it's I think that's an important point. Yes, it's a simplification that was made for that particular subsystem, and the motivation behind that simplification is basically because at that particular point in time we had the performance data for just the whole compressor package, basically. So we basically represented the single stage compressor because, one, it was not considered as a critical system for that particular study, and in addition, the design information that was available at that point in time was for the whole compressor package. PSC has experience representing full compressor flow sheets with multi-stage compressors and can offer those kind of services if required. But at this particular point in time, it was the decision was made to represent the compressor section with just a single stage.
Yeah, I mean, sorry, I guess if I just jump in quickly. I suppose the main thing was to do with the timing, because I mean the FEED study was a massive undertaking by Shell, and the timing of the different deliverables just meant that as we were putting together the model, we didn't have the details of the proposed system.
Okay, thank you. What happens to the temperature in the well on shut-in? How far does it drop? Is that something you modelled that you'd have an answer for?
That's a good question. It's something we modeled, and we didn't present that in this particular slide. Well, because of the closure of the choke valves, you have some geothermal effects, so the temperatures typically drop. What you observe with time is that in the well itself, due to the geothermal effects, you have the effects of the surrounding formation heating up the fluids in the well. So you actually get a temperature rise over time. And what we found was that for the time period within which we considered the startup and the shutdown operations, that effect wasn't hugely significant. Or what we did see, obviously, was the temperature drop, which was one of the things that was closely monitored.
Thank you, Adi. Regarding the metric, clean electricity, was that based on the amount of CO2 captured or the CO2 emissions avoided? That's what would be taking into account the parasitic load of the capture plant?
Okay, so I'll answer this one. Basically, we tried to match as close as possible the commercial agreement for the clean electricity, which actually is kind of still being negotiated. But part of the issue is it's on the amount of CO2 that is sent into the pipeline, and this is just down to the accuracy of measurements. So ideally it would be to directly measure the emissions and try to limit those as much as possible, but it's very difficult to measure the amount of CO2 in the gas going up the stack, and the accuracy wouldn't be close enough to put any sort of commercial agreement on it. So what we do is we calculate the amount of CO2 that's produced, because the amount of fuel going into the plant is obviously very closely monitored, and then we also measure the amount of CO2 that is being sent into the pipeline. So those two numbers then give you a percentage for your capture rate, which is the one that's used for the clean electricity.
Okay, thank you, Penny. Can you give an indication of the amount of additional CO2 that can be captured during startup and shutdown with the improved procedure, perhaps as a percentage increase?
We can't really give the numbers. I mean, you can sort of see from the graphs from a kind of a baseline position, which is starting from 0% capture for most of the startup until you actually begin the capture plant. When you compare that with, I guess this will probably be more useful for you looking at the presentation later. But so you can kind of compare that to how much we've moved towards that dotted line, which would be, rather than starting from no capture, starting from 90% capture, and we can get most of the way there in most of the cases. So for just looking at a startup and a shutdown, it was certainly very significant.
And I'll just add that we do hope that in the future there'll be more information that we could make available.
We're coming to the end of the time we have scheduled for our webinar this morning or today. I just want to ask one final question. What other type of capture systems can be modelled with the PSE tools that are built into this package?
Mm-hmm. Yeah. At the moment, we have we cover absorption processes, and this both for chemical and physical absorption. We have a database of solvents that are, let's say, more or less typical, and also we work with technology developers for their specific solvents. Obviously, this won't be part of the main tool, just simply because we're bound to confidentiality with them. But let's say all traditional solvents, from MEA to Selexol, Frectisol, MDA, processing, they will be they are included in the database. We're also looking into extending the capture technology models. Areas that we actively are working at the moment, adsorption, and for example, we have a project together with Centev, Politecnica Milano, University of Belgrade, other partners. Please excuse me if I didn't get all of the partners in the line, but we're looking there at electric swing adsorption. There, Centev is the leading partner on that. We provide the modeling to the University of Belgrade. And then obviously chemical looping is something that is relevant to us as well, because we do see the value on industrial CCS as well. And we work already with a number of cement companies providing simulation and modeling services for their cement plant. So the next logical step for us is also to expand to industrial CCS.
Thank you.
Perhaps I just realized right now, I've only mentioned the post-combustion technologies. We also have molds for oxyfuel and also for gCCS power plants, so also pre-combustion in the sense of gasification and then using, for example, Selexol to capture the CO2 before the combustion process.
Thank you, Alfredo. Unfortunately, we weren't able to get through all the questions in the allowed time. I apologize for the problems with the IT. That's one of the risks of broadcasting live, unfortunately. However, if you still have questions, please feel free to submit them to the Institute through our webinar inbox, the address for which is visible on the screen. It's webinar@globalccsinstitute.com. This webinar has been recorded and it will be made available on our website along with a copy of the presentation in the coming days. I would like to close by thanking our presenters, Alfredo, Adekola and Penny, for taking the time to present today. This is one of a series of expert webinars that are presented by the Global CCS Institute. I would encourage you to come back and keep an eye on our future program. I hope you found the webinar today interesting and valuable. Finally, as you are leaving the session today, we've put together a very quick 3-question survey that we use to improve our webinar program. We would very much appreciate it if you're able to take the time to complete it. This helps us tailor future webinars to meet the needs of our audience. Thank you all again for your attendance today, and goodbye.